Good morning to one and all. Myself, Dr. D. Sudhakar, working as Professor and Head of Mechanical Department at Siddhartha Institute of Science and Technology, Prithush. Today, we are going to start the discussion about this modern machining methods. In this modern machining methods, the present topic is related to the what is the need of modern machining methods. Technically advanced industries like aeronautics, nuclear reactors, automobiles, etc., have been demanding materials like high strength, temperature resistance alloys having strength to weight ratio. Like, for example, in case of aeronautics or nuclear reactors or automobiles, day to day, the demand for the high strength and high temperature materials requirement is more. In order to, after developing these and high hardness material and high strength material and high strength and temperature resistance material, for machining of these alloys or machining of these metals is very, very difficult by means of the conventional machining methods. So in order to in order to cut those components, these modern machining methods are very much useful. The researchers in the area of material science are developing materials having high strength, hardness, toughness, and other diverse properties. After the Second World War, the demand for these advanced materials which are having high hardness and high strength and high toughness is increases, which are very much useful in case of the aviation industry or nuclear industry or in the automobile sector. So this is also one of the need for the development of improved cutting tool materials so that productivity is not hampered. Suppose if you go these materials with conventional machine tools, it's very difficult to machine, and at the same time, even though if it is possible, it will take more amount of time to cut those components, even though we can cut, but you cannot get the required surface finish and dimensional accuracy. That is the drawbacks with the conventional machining process. So in order to overcome those problems in the conventional machining process, there is a need for the development of these modern machining methods. So it is a well-established machining, the conventional process. In case of as increase in hardness of the work material, the results in decrease in economic cutting speeds. As usually, this is a well-known fact for everybody. If the hardness of the material is increases, then automatically the cutting speed will be decreased in case of the conventional machining process. Because in case of conventional machining process, the machine tools or cutting tools are made of like high-speed steels, molybdenum-based steels, or tungsten-based steels, or nickel-based steels, or stainless steels. So these are all the different types of materials are used for the manufacturing of these tool materials. But if we use these tool materials to cut the high hardness materials, it's very problems like you are unable to get, you cannot cut the components with an effective speed. Even though if it is possible, the metal removal rate will be less and dimensional accuracy is also less. It is no longer possible to find tool materials which are significantly hard and strong to cut the materials like titanium, stainless steel, pneumonics, and similar other high strength temperature resistance alloys. The fiber reinforced composites, stellites, ceramics, and other difficult to machine materials. So these are the different materials or components which are required to be made from titanium or stainless steels, pneumonics, similar other high strength and temperature resistance alloys, and ceramics and other difficult to machine materials. These are very hard materials. These type of hard materials are not at all possible, economically not possible to cut by conventional machine tools. So for this purpose, there is a need for the development of these modern machining methods. And one more point is the production of complex shapes in such materials by traditional methods is still more difficult. So whatever the components, the difficult to machine materials are it is very much difficult to cut by the conventional machining process. Apart from that one, the production of complex shapes. So wherever there is a required to manufacture a complex shapes in such materials. Materials are already in hard manner, very hard, high hardness and high toughness and high strength. Apart from that one, in the same materials, we need to produce a or to cut a complex shapes. That is somewhat difficult. So this is also very much important requirement. In order to meet these requirements, there is a need to develop these modern machining methods. Other high level requirements such as low values of tolerances and high production rates, complex shapes and automated data transmission and miniaturization. These are all the other requirements which are all not possible by conventional machining process. All these requirements can be reached by means of this modern machining methods. That's why there is a need for the development of these modern machining methods. And making of holes in difficult to machine materials is another area where the appropriate process are very much in demand. So if you want to create a holes like a large in a difficult to machine materials with a large aspect ratio and a large number of holes, small holes in a one workpiece or contoured holes, holes without burrs, these are all somewhat difficult to produce by conventional machining process or by drilling machines. So such type of holes can be possible only with the help of the modern machining methods. Aforesaid, so these are all the characters are commonly required in the products used in industries like aerospace, nuclear industries, missiles, turbines, automobiles, etc. So all these properties, all requirements are very much important in all these industries. That's why I told these modern machining methods are very much important in aerospace industries, nuclear industries, missile industries, turbine manufacturing, and automobile manufacturing sector also. So to meet such demands, a different class of machining processes, those are called non-machining, non-traditional machining process or advanced machining process or modern machining process are have been developed. So this is all the because of all these things we need to develop a modern machining methods. There is a need for development, need for machine tool and machine by which we can accurately machine easily in difficult to machine materials to intricate and accurate shapes. So for creating or producing the intricate shapes and accurate shapes in difficult to machine materials, these modern machining methods are very much important. The machine tools should be easily adaptable for the automation as well. In order to meet these challenges, a number of new material removal process have been developed to the level of commercial utilization. So these newer methods are also called unconventional in the sense that the conventional tools are not employed for metal cutting. So whatever the conventional machine tools like lathe machine, drilling machine, boring, reaming, onslaughting, grinding, all these conventional machine tools are not useful in the case of cutting very hard materials. So because of that one, there is a need for the development of this unconventional machining process. Instead, the energy in its direct form is used to remove the material from the workpiece. The range of applications included in this was determined by the work material properties like electrical and thermal conductivity, melting temperature, electrochemical equivalents. So the applications of these modern machining methods mainly depends upon the work material properties like electrical properties of the material, thermal conductivity of the materials, melting temperature of the materials, and electrochemical equivalent of the particular materials. Some of this newly developed process can also be machined workpieces in the areas which are inaccessible for conventional machining methods. So wherever there is not possible, there is not accessible in conventional machining process. In those areas, these unconventional machining processes are very much useful. The use of these processes is becoming increasingly unavoidable and popular at the shop floor. So, because of all these requirements, these unconventional machining processes or advanced machining processes or modern machining methods are becoming increasingly unavoidable. Means we cannot avoid these unconventional machining process because that much huge demand or requirement or necessity is there in day-to-day activities and the shop floor level. So these machining processes become still more important when one consider the precision machining and ultra precision machining. So wherever we need a precision machining, accurate machining is and ultra precision machining or very high level machining or finishing or accuracy tolerance wherever it's required. In all those cases, these modern machining methods plays a very much important role. The Taguchi concluded that such high accuracies cannot be achieved by conventional machining methods in which the material removed in the form of chips. So in case of the conventional machining process, the material is removed in the form of chips, whereas in case of unconventional machining process or non-conventional machining process or modern machining methods or advanced machining process, the chips are removed in some process. In some other machining process, there is no, the chips are not visible to our eye also. However, such accuracy can be achieved by some of the advanced machining techniques whereby the material is removed in the form of atoms or molecules individually or groups. So here in case of the modern machining methods, the material is removed at a level of atoms or molecular levels. The advanced machining process can be classified into the three basic categories: mechanical, thermoelectric, and electrochemical and chemical machining processes. None of these processes is best under all machining situations. It means that no machining process is suitable for all the conditions. These machining processor we have to select based upon the requirement. Some of them can be used only for electrically conductive materials, while the others can be used for both electrically conductive and electrically non-conductive materials. For example, electrical discharge machining, wire electrical discharge machining, and electrochemical machining process. These machining process can be used to cut only electrically conductive materials. Whereas in case of laser beam machining, chemical machining, electron beam machining, plasma arc machining, ion beam machining, all these machining process can be used to cut the material even in non-conductive materials also. So this is the classifications. Before that one, the performance of this process is not very good while machining the materials like aluminum having very high thermal conductivity also. So in case of while conducting this aluminum, these non-traditional machining process or modern machining methods are not a very good useful. It's not that much useful. Also, these machining process have their distinct character features. Hence, the selection of appropriate machining process for a given situation becomes a very important thing. So as an engineer, we should be in a position, depending upon the requirement, depending upon the situation, depending upon the economical conditions, by considering all these factors, we have to select a right machining process for a right material in the right place. Now coming to the classifications of this advanced machining process or modern machining process. So as I already discussed, these modern machining methods or advanced machining techniques can be broadly categorized into mechanical, energy based, mechanical, thermoelectric, and electrochemical and chemical. Under this mechanical process, the process come under this mechanical energy uses are abrasive jet machining, ultrasonic machining, water jet machining, abrasive jet machining, abrasive flow machining, and magnetic abrasive machining. Under the thermoelectric machining process, the plasma arc machining, laser beam machining, electron beam machining, electric discharge machining, and ion beam machining. Under this electrochemical and chemical machining process, the electrochemical machining ECM, chemical machining CHM, and biochemical machining process. Like this, the entire modern machining processes or advanced machining process are broadly come under the three categories. Those categories are like mechanical, thermoelectric, and electrochemical and chemical. Now coming to the differentiation between the conventional machining and non-conventional machining process. Coming to this differentiation, first of all, in case of conventional machining in the first column, and it is a non-conventional machining process. In case of the conventional machining process, the cutting tool and workpiece are always in physical contact with relative motion with each other, which results in friction and tool wear. In case of the conventional machining process, we are going to use, like for example, in case of the lathe machine. In lathe machine, we can use the single point cutting tool. It's made of high speed steel. And whenever you engage this tool and workpiece, there is a direct contact between the tool and workpiece. Here, the cutting tool and workpiece are always in physically contact with each other. Whenever there is a physical contact and they are more relatively with each other, then automatically friction will be developed. Because of that friction, the tool wear will be come into the picture. But in case of the conventional machining process, there is no physical contact between the tool and workpiece. See, in most of the machining process, like electrochemical machining process, like laser beam machining, ultrasonic machining, and otherwise ion beam machining, electron beam machining, chemical machining, in all this machining process, there is no physical contact between the tool and workpiece. In some non-traditional machining process, tool wear exists, especially in case of ultrasonic machining process. Coming to the point number 2, material removal rate is limited by mechanical properties of the work material. It means that the metal removal rate in the conventional machining process is entirely depends on the workpiece material properties. Like if the material is soft or ductile material, then the metal removal rate is high. But if the workpiece material is high strength and high temperature material, or high strength, high toughness, and high hardness material, then automatically the material removal rate will be reduced. But in case of the non-traditional machining process or advanced machining process or modern machining process, we can machine the difficult to cut and hard to cut materials like titanium, ceramics, pneumonics, SST, composites, and semiconducting materials. Means here, even though it's a very tough materials or hard materials or difficult to machine materials, all these materials can easily cut by modern machining methods. Coming to the next point, the relative motion between the tool and workpiece is typically rotary or reciprocating. In case of the conventional machining process, thus the shape of the work is limited to a circular or flat shapes. See, in case of the conventional machining process, mostly we are going to produce the shapes like circular shapes or flat shapes. In some conventional machine tools, we can, if you use CNC machines like a computer numerical control machines, the production of 3D surfaces is still a difficult task. But in case of a non-conventional machining process or modern machining methods, capable to produce complex 3D shapes and cavities very easily. So when comparison to the conventional machining process, in non-conventional machining methods or modern machining methods or advanced machining process, we can capable to produce a complex 3D shapes and cavities very easily when comparison to the conventional machining process. This coming to the next point, the machining of small cavities, slits, blind holes, through holes are difficult in case of the conventional machining process. But in case of the non-conventional machining process, the machining of small cavities, slits, production of non-circular, micro-sized holes, large aspect ratio of holes shall entry holes are easily machined by non-traditional machining process or modern machining methods. Coming to the next point, use relative simple and inexpensive machinery and readily available cutting tools. So in case of the conventional machining process, the machine tools or components or machines are relatively somewhat inexpensive machinery, and they are readily available cutting tools. Whatever the cutting tools available in the market or in our shop floor, we can use those cutting tools, and the cost of those cutting tools are also somewhat less, and those machine tools can be easily used. But whereas in case of the non-conventional machining process, it requires expensive tools and a very high skilled labor is required, which increase the production cost significantly. So because of the too expensive tools and because of the high skill labor is requirement, the cost of this machining process is more, then automatically the production cost of the component will be increases significantly. Then coming to the next point of this conventional machining process, the capital cost and maintenance cost is low. So in case of the conventional machining process, the initial cost of the machine and capital cost of the machine is somewhat low. But whereas in case of the modern machining methods or advanced machining process, the capital cost and maintenance cost is also high. Next, another point in the conventional machining process is traditional processes are well established and physics of the process is very well understood. So since from the first industrialization, the machine tools were developed a lot. All these conventional machine tools are understood very well. So because of that process, how exactly the process will be takes place, and how exactly the machining will be takes place, and how the material will be removed, and how the heat will be generated, and how the heat will be distributed, and what will be the effect on the cutting tool, and what will be the effect on the tool, like that everything well established. The physics of the machining process is well established or well understood in case of the conventional machining process. But in case of the non-conventional machining process, still the physics of the material removal is still under research only. No one is understood perfectly how exactly the machining will be takes place, how exactly the heat transfer will be takes place in between the different components in the machining process. All those things will be still under the research only. Next, coming into the conventional machining process, and this conventional machining process mostly uses the mechanical energy. But whereas in case of non-conventional machining process or modern machining methods, apart from the mechanical energy, we can use laser energy, electron beam energy, the direct and laser beam energy in case of the laser beam machining and electron beam machining respectively. Now, in case of the conventional machining process, the surface finish and tolerances are limited by machining inaccuracies. So, if something is, in case of the conventional machining process, whatever the surface finish and tolerance are limited because of this machining inaccuracies. If something goes wrong, automatically it will affect on the surface finish and tolerances of a particular component. In case of this non-conventional machining process, high surface finish up to 0.1 microns and tolerances up to 25 microns can also be achieved. And in case of the conventional machining process, the main advantage is like high metal removal rate is possible. And whereas in case of non-conventional machining methods or modern machining methods, the metal removal rate is somewhat low when compared with this conventional machining process. Now coming to the advantages and disadvantages. First, we'll discuss about the advantages of this modern machining methods. It provides high accuracy and surface finish when comparison to this conventional machining process. And another point is no physical tool is used, hence no tool wear occur in the process. So in case of the laser beam machining, ion beam machining, electron beam machining, chemical machining, in all these advanced machining process, no physical tool is required. So if there is no physical tool or no tool wear is coming to the picture. Next one. They do not generate chips or generate microchips. In advanced machining process or modern machining methods, in some machining process like abrasive jet machining, water jet machining, and ultrasonic machining, in these three machining process, chips will be generated. But in remaining cases like laser beam machining, electron beam machining, ion beam machining, chemical machining, in all these machining processes, the chips will not be formed. and these are quieter in operation. These modern machining methods during the operation and the sound pollution is somewhat less and very quieterly we can operate these machines. And another point is these modern machining methods can be easily automated when compared to the conventional machining tools. Next, these unconventional modern machining methods can be used to cut any work material irrespective of their hardness and even irrespective of the shape also. So complex shapes can also easily cut by means of this non-conventional machining process or modern machining methods. Now coming to the disadvantage like high initial cost or setup cost. So comparison to the conventional machining process, these modern machining methods initial cost is more. And in order to run these modern machining methods like advanced laser beam machining, electron beam machining, electrochemical machining, or electrical discharge machining, wire electrical discharge machining, ion beam machining, chemical machining, and others. In order to operate, in order to process these machining tools, very high skilled labor is required. That is also one of the disadvantages when compared to the conventional machining process. Means if the high skilled labor is required, we have to pay the more salary when compared to the conventional machining process. And one more disadvantage of this advanced machining process is lower metal removal rate. So when comparison to the conventional machining process, in modern machining methods, the metal removal rate MRR is less. Now we are going to discuss about this ultrasonic machining process. The ultrasonic machining process is one of the non-traditional machining process in which abrasives contained in a slurry or driven against the work by a tool oscillating at a low amplitude, that is 25 to 100 microns, and a high frequency 15 to 30 kilohertz. So this ultrasonic machining process is one of the non-traditional machining process in which we are going to use the slurry in between the tool and workpiece, and the tool is oscillating in forward and backward direction. The amplitude of this tool oscillation is 25 to 100 microns, and the frequency at which we are going to move this tool is 15 to 30 kilohertz. Now coming to the working principle of this ultrasonic machining process. The ultrasonic machining is a subtractive manufacturing process that removes material from the surface of a part through high frequency, low amplitude vibrations of a tool against the material surface in the presence of a fine abrasive particles. It means that here we are going to use a tool, whatever that shape you want to produce on the workpiece, the same shape of the tool you have to manufacture, and that tool is used. In between the tool and workpiece, we are going to supply the slurry, and this tool is moves in the forward and backward direction at high frequency and low amplitude. Means the distance movement move towards the backward and forward and upward direction is very less, but the frequency is more. Means number of times it is move forward and coming backward in a fast manner. In between these tool and workpiece, we are going to supply the abrasive particles. So this is the diagrammatic representation of ultrasonic machining process, and this one is the tool cone, and this one is the tool tip, and this tool is going upward direction and downward direction, and this is the workpiece, and here this is the nozzle through which we are going to supply the abrasive fluid or abrasive slurry. So this is the diagrammatic representation. The bottom portion is the workpiece, and this top portion, this is the tool holder, and this one is the tool. See, whatever the shape of the tool is here, the same shape will be reproduced in the workpiece. In between this tool and workpiece, we are going to supply the abrasive particles. These abrasive particles are having the sharp edges. Whenever this tool applies the pressure on these sharp abrasive grains, those abrasive grains will be crushed, and whatever the sharp corners are there for these abrasive grains, again it will hit the surface of the workpiece so that it removes the material from the workpiece. So the energy required to move this tool in the forward and backward direction means to oscillate this tool in the forward and backward direction. It comes from this ultrasound, coming from this electrical circuits, and this is the voltage of ultrasonic frequency is the transformer, and this is the transducer, and these transducers will get the energy from this circuit. So the main purpose of this transducer is to convert the electrical energy into mechanical energy. The same mechanical energy is transferred to this silver shoulder joint, their transducer cone, and then this is the resonance support. Finally, this entire energy will be transferred to this tool, and the tool will be moved in the forward and backward direction with a high frequency. And because of that one, the material is removed from the workpiece, and those material removed from the workpiece is flushed out along with this abrasive slurry when it is passing supply through this nozzles. So this is again one more diagram to represent how the machining takes place in case of the ultrasonic machining process. And the bottom one is the hatching, one is the workpiece. Previously, it is a completely rectangular shape, and this is the tool which is connected to the tool horn. And in between this tool and workpiece, we are going to supply the abrasive slurry of abrasive and water. And here the vibrating frequency is about 19 to 25 kilohertz, and amplitude is about a 10 to 50 micrometer. So this tool is oscillates with help of this force, and it will go in the forward and backward direction. So this is also this diagram is also will give the same information about this, how the machining will be takes place in case of the ultrasonic machining process. Now coming to this explanation of this process, the ultrasonic machining is a mechanical type non-traditional machining process. So this is come under the mechanical type machining process, and this UVSM ultrasonic machining process is employed to machine hard and brittle materials. Both electrically conductive materials and non-conductive materials. So this ultrasonic machining process can be used to cut both electrically conductive materials and non-conductive materials also. The materials which are having high hardness, usually greater than 40 HRC. This process was first developed in 1950s and was originally used for finishing of EDM surfaces. Means whatever the components are produced by electric discharge machining process, and that machining components having some burrs, or if you want to remove very small amount of metal from the workpiece, those burrs are removal of small material. This ultrasonic machining is used with the help of abrasive slurry. In ultrasonic machining, the tool of a desired shape vibrates at ultrasonic frequency of 19 to 25 kilohertz. So whatever the tool or whatever the shape you want to produce on the workpiece, that tool is prepared and it is made to vibrate at a frequency of 19 to 25 kilohertz with the amplitude of 15 to 50 microns over the workpiece. Generally, the tool is precede down with a feed force F, means the tool is forced to move in the downward direction. After machining, it will come back again, go down, like this is a continuous process going downward by coming forward. There is oscillative force. Between the tool and workpiece, the machining zone is flooded with hard abrasive particles, generally in the form of water-based slurry. See, in between this tool and workpiece, we are going to supply the abrasive particles with help of water. It becomes a slurry, and those slurry is supplied with help of nozzle in between the tool and workpiece. That is the machining zone. As the tool vibrates over the workpiece, abrasive particles acts as indenter, and the indent both the work and tool material. Means, well, as the abrasive particles are sharp edges, when this tool come and apply the force on the top of this abrasive grains, and somehow it also these sharp edges will also indent on tool surface, and whatever the sharp edges is there on the bottom of these sharp grains, it will also indent on the workpiece material also. The thing is, these because of these sharp edges, very less amount of material is removed from the tool. Means the tool wear is very less when comparison to the material is removed from the workpiece. Means the material removed from the workpiece is more very high when comparison to the tool wear rate. The abrasive particles as they indent, so means whenever it indent on the workpiece material, would remove the material from both tool and workpiece. As we already discussed, when it is indent on both workpiece and tool, it removes the very small amount of metal from the workpiece and huge amount of metal from the workpiece and very small amount of metal from the tool. In ultrasonic machining, the material removal is due to crack initiation, propagation, and brittle fracture of the material. Means whenever the sharp edge indent on the surface of the workpiece, there are three things will come into the picture. Those things are: first, crack will be generated, means crack initiation, and the crack will be moved. It's a propagation, and immediately the brittle fracture of the material will be takes place. The ultrasonic machining is used for the machining of hard and brittle materials, which are poor conductors of electricity and thus cannot be processed by the electrochemical machining or electro discharge machining. Means this electrical discharge machining, this ultrasonic machining process is mainly used for the machining of non-conductive materials. They are the bad conductive materials which are having very hard and brittle properties. So these non-conductive materials are not possible to cut by electrochemical machining process, electrical discharge machining process. That's why these materials are mainly used to cut by ultrasonic machining process. Now, the tool in USM is made to vibrate with a high frequency onto the work surface in the midst of the flowing slab. So the tool is oscillate or made to vibrate with high frequency, means number of times it will go forward and backward direction within the unit time. So the main reason for using the ultrasonic frequency is to provide better performance. So in order to provide the better performance, we are going to use this ultrasonic frequency, that is 19 to 25 kilohertz. The audible frequencies of required intensities would be heard as extremely loud sound and would cause fatigue and even permanent damage to the auditory apparatus. Now coming to the process parameters, what we are going to use in ultrasonic machining process, means that is the process parameters. The main important process parameters we have to consider in this ultrasonic machining process is like amplitude of vibration. So at how much distance the vibratory tool has to go in the forward and backward direction, means 15 to 50 microns. The frequency, number of times per unit time, 19 kilohertz to 25 kilohertz. Next, feed force related to the tool dimensions. And then feed pressure, with how much pressure we have to give this tool, and then abrasive size and means depend this abrasive size also plays a vital role in removing the material from the workpiece and surface of the finish of the workpiece and accuracy of the surface produced in the ultrasonic machining process. So we have to select properly. Then abrasive materials. The abrasive materials like aluminum oxide Al2O3, silicon carbide, boron silica carbide, and diamond. These are the different types of abrasive grains we can use in this ultrasonic machining process. The flow strength of the work material, and then flow strength of the tool material, the contact area of the tool, the volume concentration of the abrasive slurry in water slurry means how much quantity of abrasives we are going to add to the water. It's also effect on the surface roughness, and it also affects on the metal removal rate and accuracy also. Now coming to the tools, the material tool, what type of materials we are going to use for the manufacturing of those tool, and the shape of the tool, amplitude of the vibration, frequency of the vibration, and strength of the developed tool. These are also considerable parameters while selecting this tool. And then work materials, what type of work materials we are going to cut by means of this abrasive ultrasonic machining process. So we have to select properly, and what is the impact strength of that work material, and what is the surface fatigue strength of the work material. Depending on the material properties of the workpiece material, we have to select concerned tool material, abrasive slurry, and abrasive flow rate, all those things. Now coming to the slurry, what type of slurry we have to use in ultrasonic machining process, like abrasives, what type of abrasives? The abrasives, while selecting the abrasives, we have to consider what is the hardness of the abrasives, what is the size of the abrasives, what is the shape of the abrasives, quantity of the abrasives flow means how much quantity of abrasives we have to flow, insert in between the tool and workpiece, and what type of liquid we have to use, the chemical properties, viscosity and flow rate of the liquid while combining with the abrasives, and how much pressure we have to supply, and how much density means how much quantity of abrasive grains we have to add to this liquid slurry. These are all the parameters plays an important role in ultrasonic machining process. Next, process capabilities means what is the capabilities of this ultrasonic machining process. And this ultrasonic machining can be machined workpiece other than 40 HRC to 60 HRC, like carbides. It can be cut the carbide workpiece or ceramics, tungsten glass, and that cannot be machined by conventional machining methods. So all these materials are non-conductive materials, and apart from this non-conductive material, non-conductive property, these materials are also having high hardness and high toughness and high strength materials also. So these materials are very much difficult to cut by conventional machining process. That's why we can use this ultrasonic machining process to cut or to machine these difficult to machine materials. Next, we can obtain a tolerance range from 7 microns to 25 microns in case of the ultrasonic machining process. And holes up to 76 microns can be drilled. Hole depth up to 51 mm can have been achieved easily. And hole depth of 152 mm deep is achieved by special flushing technique also. So deep hole drilling, if the depth of the hole is more high, then automatically it is very difficult to cut by conventional machining process. So such high depth holes can easily cut by means of this ultrasonic machining process. The aspect ratio is up to 40:1 has been achieved by means of ultrasonic machining process. The linear metal removal rate is 0.025 to 25 mm per minute. I mean, this much quantity of movement is tool will be moved on which the material we can remove per minute. The surface finish obtained in this ultrasonic machining process is 0.25 microns to 0.75 microns. Then these ultrasonic machining process is also used non-directional surface texture is possible. And compared to the conventional grinding, When comparison to the conventional grinding, it has to move in only in one direction. But whereas in case of the ultrasonic machining process, you can move the tool in any direction. In radial overcut may be as low as 1.5 to 4 times the mean abrasive grain size. So this is the graphical representation of the effect of process parameters on metal removal rate. Means if the force is more and how it is going to affect on metal removal rate. If the force is increases automatically up to some extent, the metal removal rate will be increases and again it will come going, it is showing in the downward direction. Means up to some extent only we have to increase the force. You should not increase constantly. If continuously you increase the force, automatically the metal removal rate will be reduced. Then coming to this area, the area of the nozzle is more, then automatically more amount of material, more amount of abrasive slurry is flow in between the tool and workpiece, then metal removal rate will be increased. Now coming to the metal removal rate. Here we are going to use two types of techniques in order to measure the metal removal rate in the advanced machining process. Those mechanisms are like throwing of abrasive grains and hammering of abrasive grains. And third one is cavitation in the fluid medium arising out of ultrasonic vibration of the tool. And fourth one is chemical erosion due to the micro agitation. The third and fourth one is very negligible when compared to the first one and second one. That's why the third and fourth one is completely neglected. So the grain, through the grain throwing model, the MRR, this is the formula for the MRR. By means of this formula, we can measure the metal removal rate in this throwing mechanism. Now coming to the applications of this ultrasonic machining process, the applications of includes the machining of cavities in electrically non-conductive ceramics. So in case of the non-conductive ceramic materials, we can easily produce the cavities by means of this ultrasonic machining process. Used to machine fragile materials in which otherwise the scrap rate will be high. So all these fragile materials can easily cut by means of this ultrasonic machining process. And this is used, this USM ultrasonic machining process is used for multi-step processing of fabricating silicon nitride turbine blades. And large number of holes of smaller diameter, that is 930 holes with 0.32 mm diameter has been reported using hypodermic and needles. And it is also used for machining of hard, brittle, hard, brittle materials and metallic alloys, semiconductor materials, glass materials, ceramic materials, and carbide materials. So these are all the applications of this ultrasonic machining process. Then some more applications are like it is used for the machining of round, square, irregular shaped holes and surface impressions. And it is also used for the machining of the dies for wire drawing, punching and blanking operations. And this is also can be used to perform machining operations like drilling, grinding, milling operations in all the materials which can be treated suitably with abrasive grains. So these USM ultrasonic machining process can be used to perform machining operations like drilling, grinding, milling operations in almost all materials which can be treated suitably with abrasive. So whichever is possible to cut with the help of these abrasive particles, all those materials can be cut by means of this drilling, grinding, milling operations. And USM can be also be used for piercing of dies and for potting of and blanking operations. The ultrasonic machining process enables a dentist to drill a hole on any shape on teeth without any pain. So this EVSM is also useful in dental applications. These ferrites and steel parts, precision mineral stones can be machined by ultrasonic machining process. EVSM can be used to cut industrial diamonds. And this EVSM is also used for grinding quartz, glass, and ceramics. Coming to this advantage of this ultrasonic machining process, it can be used for machining of the hard, brittle, and fragile and non-conductive materials, and no heat will be generated in work. Therefore, no significant changes in physical structure of the work material. And non-metal that cannot be cut by in EDM or ECM can also be cut by means of this ultrasonic machining process, and it is a burless and distortionless process, and it can be adapted in conjunction with the other new technologies like electric discharge machining, electrochemical grinding, and electrochemical machining process also.